Hello friends. Today we will discuss the transient heat conduction. What is transient heat conduction? Let us see the equation, that is del square T upon del x square plus del square T upon del y square plus del square T upon del z square plus G dot divided by K equal to rho C divided by K into dt by dt. We have already gone through a general heat conduction equation in a Cartesian coordinate system, and this is what represented over here, that this is a general heat conduction equation in Cartesian coordinate system. Up to last lecture, whatever we have considered is a steady state condition in which we have not considered the heat transfer with respect to time. This is certainly simplify the analysis, especially when the temperature varied in one direction only and we were able to obtain the analytical solution. In this particular chapter, we consider the variation of temperature with time as well as position in one and multiple multidimensional systems. Let us understand the phenomena. Transient heat conduction. We start this chapter with the analysis of lump systems in which the temperature of a solid varies with time but remains uniform throughout the solid at any time. So in this particular system, we assume that we are having a solid. The temperature of solid will remain uniform throughout the time, but with respect to time, the temperature will vary. I repeat, in this lump system, in which the temperature of solid varies with time but remains uniform throughout the solid at any time, we consider. Then we consider the variation of temperature with time as well as position for one-dimensional heat conduction problems, such as those associated with the large plane wall, a long cylinder, a sphere, and a semi-infinite medium, using transient temperature charts and analytical solutions. Finally, we consider the transient heat conduction in multidimensional system by utilizing the product solution. This is the flow of our chapter. We will discuss one by one. Let us understand the lump system analysis. You can see here two figures are mentioned. One is a copper ball and its temperature is uniform throughout 70 degrees Celsius. Second is a roast beef is given, and the temperature you can see here, the temperature is 110 outer surface, approximately in the middle is 90 degrees Celsius, and innermost surface temperature is 40 degrees Celsius. Let us see. In heat transfer analysis, some bodies are observed to behave like a lump whose interior temperature remains essentially uniform at the all times during a heat transfer process. This is this condition. The temperature of such bodies can be taken to be to be a function of time only. Heat transfer analysis that utilize this idealization is known as lump system analysis, which provides great simplification in certain classes of heat transfer problems without much sacrifice from accuracy. Look at this figure. Some arbitrary shape is given and it is a solid body whose mass is m, volume is capital V, density is rho, and initial temperature is Ti. Its surface area is A suffix S, convective heat transfer coefficient is H, and ambient fluid temperature is T infinity. Consider a body of arbitrary shape of mass m, volume V, surface area As, density rho, and specific heat Cp initially at uniform temperature at Ti. So we assume that this body temperature initially is Ti, which is mentioned here. At time t equal to 0, the body is placed into a medium at temperature T infinity and the heat transfer takes place between the body and its environment. With the heat transfer coefficient H, for sake of discussion, we have we will assume that T infinity is greater than Ti. So you can consider when T infinity is greater than Ti, you can consider the example of oven. You are cooking something in an oven where uh, T infinity is your oven temperature, which is high, and Ti is your food temperature, that is Ti. But the analysis is equally valid for opposite side. You can assume a different case conditioning condition like casting, where object is a hot and you put this object into a surrounding which is having low temperature. So both case, this will work. We assume lump system analysis to be applicable so that the temperature remains uniform within the body at all times and changes with time only. That is, T is function of time only. During differential time interval delta T, the temperature of body rises by a differential temperature dt. An energy balance of the solid for the time interval dt can be expressed as the heat transfer into the body during time dt is equal to increase in the energy of the body during time dt. So we can write this equation H A Ts minus T infinity into dt will be equal to mcp dt. Noting that mass is nothing but density into volume, and dt change in a temperature is whatever temperature at time minus T infinity, that is ambient fluid temperature, which is constant. So we can write this equation equal to d T minus T infinity divided by T minus T infinity will be equal to HAS rho VCP into dt. Now integrating from T equal to 0, at which T equal to Ti, initial temperature of our solid is Ti, to any time T at which T will be equal to Tt. So when you integrate and put it into equation, the equation comes to ln. Anytime your temperature will be at T minus T infinity divided by initial temperature Ti minus T infinity will be equal to minus H As divided by rho V Cp into T. Taking the exponential of both sides and rearranging the equation, we will get the equation that is T bracket T is any time temperature of object minus T infinity divided by initial temperature minus T infinity will be equal to e raised to minus bt, where B is nothing but H As divided by rho V Cp is positive quantity whose dimension is time inverse. The reciprocal of B has a time unit, usually S, and is called by a time constant. This equation 4 is plotted in a figure. Right side you can see for different value of B, there are two observations that can be made from this figure and relation above. You can see here the plot is time versus Tt. So when times changes, what will be the change in of temperature we are plotting over here. Our T infinity is constant and that line is plotted over here. Our T initial point is somewhere over here. Now the graph shows that how your B changes, your graph changes. The equation 4 enables us to determine the temperature T bracket T of a body at time T, or alternately the time T required for the temperature to reach a specific value of T. If time is known to you, you can calculate temperature. If temperature, what temperature we will get within that time, you can calculate time also. So vice versa, we can calculate. The temperature of a body approaches the ambient temperature T infinity exponentially. The temperature of the body changes rapidly at the beginning, but rather slowly later on. A large value of B indicates that the body will approach environment temperature in a short time. Means heat transfer will be faster. The larger the value of exponent B, the higher the rate of decay in the temperature. Note that B is proportional to the surface area but inversely proportional to the mass and specific heat of the body. This is not surprising since it takes longer to heat or cool a large mass, especially when it has a large specific heat. So any object which is having large specific heat, it will take longer time to be heated up or to be cooled. Once the temperature at some time T is available from equation 4. The rate of convection heat transfer between the body and its environment at that time can be determined by Newton's law of cooling, as we know, Q equal to H A T minus T infinity. The total amount of heat transfer between the body and the surrounding medium over the time interval t equal to 0 to t is simply change in the energy content of the body, that is mCp delta t, and the amount of heat transfer reaches an upper limit when the body reaches the surrounding temperature. Therefore, the maximum heat transfer between the body and surrounding is Qmax equal to mCp delta T, which is T infinity is surrounding temperature and T is initial temperature. We could also obtain this equation by substituting Tt relation into equation 4 into equation Qt relation to 6 and integrating from T equal to 0 to T infinity. Okay, so we have gone through that how this lumped system analysis works. Now we will understand the criteria for lumped system analysis. As you have seen in this equation, that this equation depends on A, surface area, convective heat transfer coefficient H, rho, V and Cp. So the lumped system analysis certainly provides great convenience in a heat transfer analysis, and naturally we could like to know when it is approximate to use it. The first step in establishing the criteria for the applicability of the lump system analysis is to define the characteristic length, and characteristic length, as you know, that is LC is volume divided by surface area. So if we consider this particular figure, suppose it is a sphere, then you need to calculate volume of sphere, area of sphere, that will be characteristic length. And second criteria we should consider here is a Biot number, and that is nothing but H LC divided by K. So it depends on characteristic length, convective heat transfer coefficient and conductivity of the material. The Biot number you can define in this way also. It is a heat convection divided by heat conduction. Now you can see this figure that a spherical copper ball is given whose conductivity is given 401 watt per meter Celsius. Diameter is given 12 centimeter. Convective heat transfer coefficient is given 15. So we can calculate LC of this, that is V upon AS, and it comes to 0.02 meter. The Biot number comes to H LC divided by K, and it comes to 0.00075, which is less than zero point 0.1. Why we have compared it with less than zero point 0.1, we will discuss. You can see here the equation. It depends on this criteria H, AS, rho, V and Cp, and Biot number is HL by K. If your K value is maximum, means your material is superconductive, your denominator value will be maximum, then your Biot number value will be minimum. So when any solid object we consider, if its conductivity is infinite, your Biot number becomes 0. And if your Biot number equal to 0, your heat transfer rate will be maximum, and you can go for this equation that is called a lump system analysis. When your conductivity decreases and specific heat increases, your Biot number changes. So when Biot number is 0, the heat transfer is maximum and you can use this equation. But when your conductivity is decreasing, specific heat is increasing, your Biot number is increasing, then this particular system, lump system analysis, will not give you accurate result. So for a better approximation, it is generally accepted that the lump system analysis is applicable if your Biot number is less than 0.1, because we have assumed that the surface of our object having uniform temperature at any time. So that is why if you want to use the lump system analysis, you need to calculate first the Biot number. If Biot number is less than 0.1, it will be applicable. In next lecture, we will solve some numerical problem using lump system analysis, so that we will understand that how to apply this method and when to apply this method.